Hello everyone, and thank you for joining this session. Today I am thrilled to present our work titled AniCrossDim, Integrating Cross-Dimensional Interaction into Desktop Character Animation Workflows. This is a collaborative effort from Shanghai Jiaotong University, the Chinese Academy of Sciences, and Lenovo. Here is a quick roadmap of my presentation. I will start by introducing the background and motivation behind our work. Then, I will introduce the AniCrossDim system, including our novel input devices and display setup. After that, we will look at how this integrates into a real animation workflow, followed by the results of our user evaluation. Finally, I will share some design implications and our thoughts on future directions. Let's put ourselves in the shoes of a 3D character animator. Their daily work is inherently hybrid. They constantly reference 2D materials like storyboards while manipulating 3D rigs to create poses. However, traditional desktop tools severely interrupt this creative flow. Because animators are constrained by 2D screens and a 2° of freedom mouse, they are forced to mentally map 2D inputs to 3D space using complex UI widgets like rotation gizmos. This indirect manipulation is unintuitive. To make a single spatial adjustment, they have to constantly switch between different camera views and interaction modes. Currently, animators are caught between two worlds. On one hand, traditional desktop UI is like Maya or Blender, offer pixel-perfect precision, but lack a true sense of spatial embodiment, forcing those frequent mode switches. On the other hand, immersive VR interfaces provide fantastic 3D intuition, but suffer from lower precision due to hand jitter. Furthermore, transitioning to immersive UI presents a steep barrier. This isn't just a learning curve. The animation industry relies on a deeply entrenched software ecosystem, and animators have years of muscle memory tied to desktop workflows. The core question driving our research is, can we have the best of both worlds in one unified workspace? Previous research has explored this gap through two main avenues. The first is transitional interfaces, which try to bridge separate hardware environments. For instance, Switch Space introduces context-aware peaking to reduce disruptive full-context switches. Traversing Dual Realities examines object-centric transition techniques between desktop and AR, while BShare augments AR head-worn displays with smartphones. The second avenue is DOF expanding controllers. In the commercial space, we see professional devices like the Space Mouse. In the research space, Handover unifies mouse-based precision selection with hand-tracked 3D manipulation in XR. We must also highlight HiFinBall, an important prior work that successfully coupled 2D and 3D interaction modes on a desktop VR setup, which relied on custom-built two-handed 6DOF control balls. In contrast to these approaches, our goal was to achieve seamless transitions using familiar commodity devices in a single workspace, without requiring users to manage parallel hardware contexts or learn entirely new bespoke gadgets. To achieve this, we established three core design goals. First, the system must support both 2D editing and 3D posing, allowing seamless movement between planar and spatial actions. Second, the workspace must be unified. We want to keep the 2D UI and 3D viewport co-located. Third, the interaction paradigm must be fatigue-aware and intuitive. We want to eliminate explicit UI toggle buttons, making the transition fast, learnable, and physically comfortable. Meet AniCrossDim. Our system pipeline consists of three main pillars. First, the hardware. We augment input devices to support 6° of freedom while preserving the traditional desktop grip, paired with an auto-stereoscopic display. Second, the state machine. We use a height-based detection system to enable implicit switching. Finally, the control logic. Resting the device triggers standard 2D mapping, while raising it activates 3D spatial mapping. Our first implementation is the DieMouse. We took a standard optical mouse and augmented it with a Vive tracker. The tracker is mounted via a rigid screw with a 2 cm gap, allowing the user to maintain their natural familiar grip. Because the tracker partially blocks the scroll wheel, we remapped zooming and scrubbing functions to the keyboard. Our second implementation is the DIM controller. Here, we took a standard VR controller and adapted it for the tabletop to give it 2D capabilities. We attached detachable 3D printed sliders to the bottom, providing 2 points of contact for a stable glide on the desk without occluding the tracking markers or interfering with the user's grip. Because raw spatial tracking can introduce slight positional jitter when mapped to a 2D screen, we applied a lightweight €1 filter to produce a perfectly stable cursor. The magic behind these devices is the implicit switching logic driven by a height-based state machine. For the die mouse, lifting it naturally stops the optical sensor from tracking 2D movement. We use a hysteresis threshold, meaning the height required to switch into 3D is slightly higher than the height to drop back to 2D. This prevents any flickering or accidental toggling at the boundary. The DIM controller is more complex because it relies entirely on spatial tracking. We had to simulate the traditional mouse lift operation, the action of clutching and lifting a mouse to reposition it on the desk without moving the cursor. To solve this, we introduced a transition mode. When the DIM controller is slightly lifted into the hysteresis zone, the cursor freezes. This decouples the spatial position from the screen, allowing users to reposition the controller on the desk just like a normal mouse. When fully lifted, it enters 6 degrees of freedom spatial mode. To complete the unified workspace, we utilize a glasses-free autostereoscopic 3D display. You might ask, why not a VR head-mounted display? HMDs isolate the user from their keyboard, cause visual fatigue over long desktop sessions, and force heavy context switches. Autostereo keeps animators firmly within their mature desktop ecosystem while providing on-demand depth cues. Crucially, the display and UI are state-coupled to the input device. When the device is on the desk, the screen shows a crisp 2D view with a traditional WIMP UI, mouse cursors, translation gizmos, and timelines. The moment the device is lifted into the air, the screen instantly switches to a 3D stereoscopic view, and the UI shifts to a spatial cursor for direct 6DOF manipulation. The end-to-end latency is at the millisecond level, ensuring perfect continuity. To evaluate ANI CrossDim, we designed an experiment grounded in real industry practices. The core task was character posing. Participants had to match a 3D character to a set of 2D reference images. This required 2D operations, like scaling and translating the reference images, alongside 3D operations, like dragging joints to pose the rig. This task perfectly mirrors real workflows while remaining structured enough for precise measurement. We recruited 18 participants for a within-subject study, counterbalanced using a Latin square design. We compared 4 conditions: a standard 2 degrees of freedom mouse, a standard 6 degrees of freedom VR controller, our die mouse, and our DIM controller. The results were highly encouraging. For accuracy, the die mouse reduced posing errors by 29% compared to the standard mouse. For efficiency, the die mouse was 33% faster than the standard mouse, performing on par with the pure VR controller. Interestingly, users switched modes significantly more frequently with the die mouse. This reflects voluntary, opportunistic use. Looking at subjective metrics, the die mouse achieved the highest system usability scale score. In terms of workload, the die mouse reduced the overall NASA TLX score by 32% compared to the standard mouse. Our study revealed several fascinating insights about how users naturally bridge 2D and 3D workflows. First, augment is better than simulate. Users strongly preferred the tracked mouse, die mouse, over the controller-adapted mouse, DIM controller. The die mouse retained the familiar, stable, and precise feel of an optical sensor. Second, frictionless switching works. The lift equals 3D, rest equals 2D paradigm felt completely natural. Because there were no buttons to press, it actively encouraged frequent, opportunistic switches. Users would freely jump between dimensions just to make a tiny adjustment. Third, ergonomics and task fit. We observed a clear biomechanical boundary. 6 degrees of freedom, spatial input is unmatched for large translations and moving objects across space. However, mid-air rotation is severely limited by the physical constraints of the human wrist. Therefore, Users naturally dropped the device back to the desk to use 2D planar input for fine rotations. We also found that 2D selection is very fast but prone to occlusion errors, whereas 3D selection is steadier but comes with a depth perception cognitive cost. Fourth, FK/IK mapping. Users naturally mapped 3D spatial input to inverse kinematics, IK for blocking, quickly grabbing and placing end effectors like hands or feet in 3D space. Then they mapped 2D input to forward kinematics, FK for polishing, resting the mouse to precisely rotate individual joints like a wrist or spine. Ultimately, the workflow beautifully condensed into a simple rhythm: lift to place, rest to refine. Of course, our work has limitations. The task scope was focused on posing and didn't include dense 2D operations like complex curve editing. The hardware prototypes also need ergonomic refinement, particularly regarding weight distribution and center of gravity. To conclude, this paper makes 3 core contributions. First, we proposed AniCrossDim, a system that seamlessly integrates planar precision editing and spatial manipulation by augmenting commodity devices, eliminating the need for hardware transitions. Second, we demonstrated its practical utility in 3D character animation workflows, seamlessly coordinating FK/IK and keyframe management. Finally, we derived a set of design implications for bridging 2D and 3D workflows. AniCrossDim proves that near-frictionless dimensional switching can successfully reconcile 2D precision with 3D embodiment, offering a low-learning overhead pathway for the future of hybrid creation tools. Thank you all for your time and attention.